Welcome. Today we're going to be talking about the binomial distribution, which is the third lesson in our Unit 6 together. And before we do that, I wanted to quickly address that a few things that are coming up. So May the 10th, okay, is our class's quiz. The quiz will be on lessons 1, 2, and 3. So distributions, uniform distributions, and then binomial distributions. Tomorrow's lesson, when we do hypergeometric distributions, that will not be on the quiz, okay? So the quiz is lessons 1, 2, and 3. I want to remind you that on the 11th, I have the CPT, or I have the computers booked rather for your CPT, so that's a very good day, again, especially if you really haven't started yet or are still kind of in the early stages. That'll be a good day to sit down and take a real bite out of this project. So it's very important that you get on that if you haven't been making much progress. The test is next Friday, okay, May the 13th. So this leaves us next week, Monday, to go over any questions. Wednesday is a work period, Thursday is a work period to prepare for the test, and then Friday is the test. So we're going to start today with the idea of a of a binomial distribution. And to do that, we're going to take a look at this situation here. This is called the Galten problem, which is where we drop a ball in and it sort of falls through, and you can see the path it took here, right? It went to the right, to the right, to the right, left, left, right, left, and then fell into this bin here, which is why this bin has a 1 and all these other ones have a 0. Typically these things are built so that there's a 50-50 probability, if we're looking here, 50% probability that the ball falls left or right. And as we run through this problem, as we do it, over and over again, so here let's do it 100 times, and you can start to see the shape of the distribution down here, that it's kind of like when we were throwing the die, right? The first option and the last option are both quite unlikely, whereas the middle options are more likely. If we continue to run this simulation a little bit further, we'll find that even after 500 attempts here in this particular sample, most of them fell into this bucket here. A lot of them fell into this bucket, and very few of them fell into the edges. Now, if we were to calculate the theoretical probability here of the ball falling into a given spot, we could do that by using techniques we've learned in the past, right? Making a sort of tree diagram that we know the ball has to make 1, 2, 3, 4, 5, 6, 7 choices, that it chooses left or right, and we basically just need to figure out how to scramble 7 L's, 7 R's, and every mixture in between. That would help us eventually work out what the probability would be down here of the ball landing in every given spot. Now we have a different way of doing this, which is I'm just going to show here with the green bars, a little bit trickier to see. But the green bars here, maybe I'll just quickly make them easier to see. The green bar here represents the theoretical distribution, right? So if you were to do this over and over and over again, right, this might be what we would expect. And just as we watch this sort of fill up again and again, so you can see here it's making the same pattern as before, right? And so on, and we just end up with this same sort of looking shape. Now before, we would always have to look at a problem like this and assume that it was always 50-50. If you think about this, we did it with like boys and girls, we did it with left and right, we did it with heads and tails. We always did these questions when they were 50-50. But what we are now going to start to look at is a different option, which is when we're talking about when it's not 50-50, right? And you can see here again, let's just take a quick look and make this a little more visible. Okay, and well, actually it's just not going to get more visible. This is how it looks, so we'll just have to deal with it. Looking here, okay, we are looking at a binomial distribution, okay? So let's set it to 50-50 just because that's what we're familiar with. And when you see the binomial distribution at 50-50, you notice it is perfectly symmetrical, right? Just like our throwing a coin or the Galten problem we were just looking at, that in a 50-50 distribution, we see that it's equally likely, right, that let's say we get a 5 or a 6, and then we might get a 7 or a 4. A 3 has the same probability as an 8, a 9 has the same probability as a 2, and so on. This is the binomial distribution. It is what we do when we are performing an experiment over and over and over again, and the experiment is either true or false. It's either pass or fail, yes or no. And if you think about the ones I mentioned before, boys and girls, right, left or right, and heads or tails, all of those are yes or no option type of questions. And that's what it means up in this part here where it says trials are called Bernoulli trials, because Bernoulli trials can be described in terms of a success or a failure, okay? And that is kind of the most important thing about this. Anytime you're looking at a probability situation where you're repeating a trial over and over and over again, but we're talking about whether it succeeds or whether it fails, we're talking about this in terms of a Bernoulli trial. We're going to say that a Bernoulli trial has a probability of success, which we're going to call P. Okay. Now, obviously, if whatever P is, right, in this case, let's say tossing a coin, success may be heads, which P is 1/2. In manufacturing, success may be something totally different. It may not be 1/2, right? It may be like a defective part, in which case the probability is a lot lower. And this is what we are going to be able to do now that we have not been able to do yet in this course, which is deal with these complicated situations when they are not 50-50. Okay, so we have P, which represents the probability of success, and then we're going to have Q, which is the probability of failure. Okay, and of course Q is equal to 1 minus P, because we know that the event either succeeds or fails, and if we add up the probability of success with the probability of failure, we should get 1. Now the probability distribution for the number of successes that we should expect, okay, is given by the binomial distribution. And this is the idea of what we're trying to accomplish here. It gives us a sense of how many successes we should expect and what the probability of getting those successes would be. So again, to quickly look back at our binomial distribution here, we could see here that if the probability of success is 50% and we are trying this thing 11 times, that it's very likely we will succeed 5 or 6 times, and not really that likely that we'll succeed 9, 10, or 11 times. Like that's too small, right? And think about flipping a coin 11 times. What are your chances of flipping all 11 heads? Is very, very small, right? That's what this is trying to capture. It's very likely that we'll have 6 successes or 5 or 4 or 7, but as we get further and further away from the middle, it's less likely. Here is the way that this thing works in terms of looking at the formula, okay? So the random variable x, right? Remember, that's the same thing that we were talking about before. The random variable represents the set of all possible outcomes. And if we go back to my picture here for the binomial again, what are all the possible outcomes? Well, I could have 0 successes, or 1, or 2, or 3, or 4, or 5, all the way up to 11, right? I'm flipping the coin 11 times. So the value that x can take on as the random variable, we'll say success is a heads, let's say. So the random variable can take on any value from 0 to 11. That would be how many successes you could have after throwing the coin 11 times. This is going to be given in terms of our calculation by this formula here. Okay, n choose x times p to the power of x times q to the power of n minus x. Now, it seems like a complicated kind of formula, but in fact, it's actually fairly straightforward. If we look at, let's go back and make a quick new sheet here for a second, and let's say we were talking about throwing 5 coins, let's say. So 5 coin tosses. Okay, let's just do a simpler example rather than working with 11 off the bat. Okay, So what are the options that we can have here? So x, let's let x equal the number of heads thrown. And it should be pretty straightforward to say that the x could be the answer, could be 0, 1, 2, 3, 4, or all 5, right? These are the choices that we have. Just quickly see what's going on here. Okay. Okay, so the probability, so let's say, just for example, we are looking at probability that x is equal to 3. What about if we were looking to throw 3 heads? How would we have solved that in the past? Okay, in the past, we would have said, okay, if you get 3 heads, right, that's head, 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 tail, tail, right? This is one way that we could throw it. Another way we could throw it is head, head, tail, head, tail. This is just another simple example, right? The question would be then, how many ways are there to do this, right? And then we need to multiply all the probabilities by each other because they're independent events, right? Throwing a coin once, you have a probability of 50%. Throwing it again, you have a probability of 50%. So throwing 2 heads in a row, right? So the probability of 2 heads in a row is going to be 0.5 times 0.5. Recall this from independent events back at the beginning of the course, right? That, when you have 2 events that occur, if they're independent, the probability of both of them occurring is to multiply the 2 events together. So our question here really becomes to get to throw 3 heads. What we need to do is we need to work out how many different ways are there to throw 3 heads, right? We need to scramble this. How many ways can you scramble 5 letters when 3 of them are H's and 2 of them are T's? And then we need to multiply the probability. This is pretty easy to do. It's 5 factorial, we know. 5 factorial over 3 factorial for the repeated h's, and 2 factorial for the repeated t's. Okay, so 5 factorial is we're scrambling 5 letters. 3 factorial is we're scrambling 3 h's, 3 identical elements, and then 2 t's becomes the 2 factorial. Now this we should recognize is the same thing as 5 choose 3, which is the same thing as saying we have 5 tosses, choose 3 heads, or 3 successes, let's say. Okay, so 3 successes there represents our the first part of the formula, right? The n choose x. N is how many times you're performing the experiment. X is how many successes you have. Now, the next part of the formula says p to the x, q to the n minus x. Okay, so the probability of a head is 0.5, and we're going to call this p. Probability of a tail is also 0.5, and we're going to call this q. Okay, so now that we do this, we simply take all our multiply. We go 0.5 to the power of 3 times 0.5 again to the power of 2. And remember, this comes from p cubed. This comes from p cubed times q squared, right? Because again, q we know was 5 minus 3, right? Which is the same thing as p cubed q squared. Okay, so what we end up with here, all right, to sort of finally to finish this one, is we end up with this part of the equation times p cubed times q squared. Okay, and then we're just going to fill in our values for p and q. Okay, and so we arrive at the conclusion 5 factorial is 120, divided by 3 factorial is divided by 6 is 20, divided by 2 is 10. So we have 10 times 0.5 to the power of 5. and